Great. Well, good morning, everybody. Thank you so much for coming and being available for my thesis defense today. My thesis is titled An Evaluation of DEM Generation Methods Using a Pixel-Based Landslide Detection Algorithm. So a background on landslides. Landslides are the mass movement of earth and or rock, usually due to an increase in moisture content. And landslides occur over varying spatial and temporal resolutions, meaning that they can be they are replicable in different kind of environmental and spatial kind of environmental and time frame kind of resolutions, and they can be mapped. And landslides need to be mapped in the U.S. because within the U.S., landslides cost about $3.5 billion a year, as well as 25 to 50 deaths. And these statistics are expected to worsen due to economic development and deforestation and things like that. So the purpose of this study was to evaluate a recent pixel-based algorithm by Xie et al. In 2018 over study areas in Washington State, and measuring how differences in DEM generation from LiDAR data affect the classification process. These three methods center around ground identification method, and spatial interpolation / void filling. A secondary goal was to assess how well the algorithm performs on different types of landslides. And this study is important because monitoring and updating landslide inventories has increasingly been involving automated landslide detection algorithms. So here we get to research hypotheses. For number one, I hypothesize that differences in the ground classification and void filling as part of the DTM generation process significantly affect the performance of the landslide detection algorithm. Number two, I hypothesize that differences in the type of landslide, which in this case were operationalized as large state inventory source landslides versus small manually delineated landslides, significantly affect the performance of the landslide detection algorithm. Excuse me. And then the third hypothesis was more focused on the actual feasibility of the algorithm itself. And so for number three is the pixel-based landslide detection algorithm by Xie et al. 2018 is an effective way of identifying landslides of varying characteristics. So now we get more into the background of information. So some techniques for mapping landslides. Traditionally, mapping landslides is considered to be expensive and time-consuming. That usually involves field work. There's been some success, but not as much as necessary for using topographic maps. But topographic maps can lack the necessary detail because of their scale. And then more recently, there's been more focus on computer-based mapping, and so computer-based mapping revolves around DEM-derived metrics such as curvature or roughness, and then you have vegetative indices such as NDVI and things like that. And then, but these methods can be overall relatively inexpensive for the actual mapping cost. Then we get into algorithmic detection of landslides. Classifiers often use what are called geomorphometric parameters to describe a land surface. These relate back to DTM-derived metrics and things like that. And these classifiers can fall into pixel-based or object-based categories. And pixel-based classifiers, which is what the Xie et al. Algorithm is, result in a salt and pepper output, which a non-continuous kind of classified surface. And then you have a object-based classifier, which create a more continuous output. These are exhibited on the image on the left side, with the left side of the image being a pixel-based and the right side being an object-based. And you can see there's definitely more spotty on the left side. So the Xie et al. Algorithm, the main focus of this, or one of the main focuses of this study, was that they examined the use of curvature and spatial autocorrelation to identify shallow landslide features. In the original study, both profile curvature and tangential curvature were used, with the Geddes or GI star statistic being used for the spatial autocorrelation, with distance weighting radii of 2 to 6 meters. And their results show that significant patterns can show landslide related features. So then you get to kind of like the nuts and bolts of this, mainly the get star GI star, because spatial autocorrelation is kind of an advanced technique and takes some understanding. And what local spatial autocorrelation is that it relies on the neighborhood variation from the global mean through distance weighting to make its determination of what is considered significant. Excuse me. So significant pixels that the technique decides is significant are returned in what are called confidence intervals. And so in Xie et al., they use both positive and negative 0.05 or 95% and 0.01 99 or 99% confidence intervals. So why use this algorithm? The algorithm was considered to be successful based on the results from the original study, mapping, I believe, about 80% of the landslides that it had attempted to map. And then this algorithm is also used due to the widespread availability of the components of the algorithm and the relative ease of replication, because I think it's a relatively simple algorithm with two working components. And so curvatures that were employed by the Xie et al. Algorithm and the spatial autocorrelation technique are available in most GIS software. So here we're kind of getting the more nitty gritty, like really nitty gritty background of stuff. And we're going to cover different types of curvature and issues in curvature calculation, as well as several interpolation and DEM generation methods. So an overview of curvature. Curvature is a primary topographic attribute that describes the rate of change of slope and the convexity and concavity of the land surface. And there are many types of curvature and formulations of each of those curvatures as well. So two major ones are profile and plan curvature, and have been instituted in several, most, if not all, GIS softwares available out there. You have profile curvature, which maps along the slope gradient, and then you have plane curvature, which maps away from the slope gradient, and so it can show convexity and concavity in both directions, in your X and Y directions. And as you can see, the left side, profile curvature it really maps the horizontal. It looks like horizontal kind of changes in curvature, and then plane curvature maps more of the drainage and valleys and stuff like that that are within the hillside. So then we get into major types of curvatures, and one major thing about curvature is that how the surface is calculated and how it's fitted to the DEM matters a lot. So for Evans 72 and 79, those a major, probably one of the original sections on curvature, or authors on curvature, uses a fitted 6 coefficient surface interpolator, basically, to help reduce the error in the calculation. Zevenbergen and Thorne, another major curvature calculation authors, uses 9 coefficients to exactly fit 9 cells in the neighborhood. And then this brings up tangential curvature, which is kind of the in-between between plan and profile. And what tangential curvature has been primarily used for is hydrological studies and mapping drainage systems. And to kind of go in more in depth in this, Minar et al. Recently in 2020, extensively looked at the differences between all these curvatures. So there are some, as technology has advanced, it has brought about some issues in curvature calculation, and especially with increased density in LiDAR, it has led to very high resolution DEMs. And since curvature is very scale dependent, meaning that a 3x3 neighborhood can be very sensitive to the noise and small microstructures that are on the Earth's surface. It can throw off these curvature calculations. And this is very evident based on the image at the right that shows the 3 different sizes of neighborhoods. So the left one is 3x3, middle is 5x5, and the right side is 7x7. And as you can see, as you move to the larger neighborhoods, you get less noise and less kind of miscellaneous data to that obscures what you're really trying to look at, is the curvature of the top and base of that looks like a volcano, based on what I'm looking at right here. And then now Esri has implemented a solution to this per se recently with their new surface parameters tool that's in ArcGIS Pro 2.7, and it allows for actually user-defined neighborhoods, so you can go up to whatever you think is necessary for the scale that you're looking at. So now we get into DEM generation. DEMs represent the bare earth surface of an area, and these are often created using LiDAR. And LiDAR recognizes any object in an area as a return, and it requires each return requires classification to find what you would consider the true ground surface. And classification can usually leave voids in the LiDAR data when you as you're about to generate these DEMs, and it requires interpolation to fill these voids as you get ready when you make DEMs. So a major one is TIN or triangular regular network, or TIN interpolation. And this is how this works is that the interpolation occurs by triangular facets of various sizes that are formed by Delaunay triangulation, where vertices are, or at each vertex is a physical measured elevation. And so these DEM voids that are then filled in a linear fashion, and this usually works somewhat, but areas of low point density, the error rates can be very high, and this is really obvious on the image at the right. On the left side of that image, you have these really obvious triangular features on the side on this hillside. And then when you run curvature calculations on it, you can really see that they really stand out, because if you look in some of the same spots that those triangles are, you see, these very obvious like triangular features with what looks like no curvature. So, and then you get into inpainting. Inpainting is a more advanced interpolation method that mimics an artist's reconstruction of damaged artwork through differential equation modeling. So a very good example of this is D'Errico's Inpainting library from 2004. Allows the use of either finite difference approach or an energy minimization technique to fill missing values. And the simple morphological filter, or SMRF algorithm, uses D'Errico's energy minimization technique as part of a ground identification and DEM generation process. And Crema et al. From 2020 found that inpainting was better for void filling than several other spatial interpolation methods, as you can see on the figure to the right. So you have DTM, which is what the original DTM is supposed to look like, and then inpainting does a very good job of smoothing out surfaces, and then you kind of get into ones that are not so good, which are spline, IDW, and kriging, and I'll cover those in a second. So some other interpolation methods, you have IDW, or inverse distance weighting, is one of the most widely used interpolation methods that and it interpolates the surface through distance weighted averages within a neighborhood. Then you have kriging, which is an interpolation method that applies local spatial autocorrelation to estimate missing values. And so on this image to the right, you can definitely see the difference between inverse distance IDW and several other types, and 4 types of kriging, with number 1 being IDW, and then 4 through 7 being kind of more progressive kriging as it goes forward, with 8 and 9 being the original 2-band and 3-band Iconos data. So And now we're getting into the methods. So kind of an overview is that for this study, we replicated the Shi et al. 2018 landslide detection algorithm over 20 study areas in Washington, in the Washington state of the United States. Landslide data sets were divided between manually digitized landslides and larger landslides that were sourced from the Washington Geological Survey, or WGS. And then the results from the landslide detection algorithm were compared across the three methods of DEM generation, as well as comparing the differences in the results between the landslide sources. So Pierce County, all the study areas were located within Pierce County, Washington, and Pierce County was chosen because it was the subject of a 2017 study that created a landslide inventory from LiDAR data. Study areas were divided between manually identified landslides and landside sourced from the WGS database, with 10 study areas belonging to each category. And so now here's a good example of a WGS sourced landslide. So you can see on the left side, there's a fresher landslide, so it's a little more hummocky and less weathered. And on the right too, it's more weathered, so they're probably older. And this represents the variability that exists within the WGS landslide database. So now we get into data sources. The LiDAR data and the LiDAR-derived DEMs for Pierce County were both downloaded from the Washington Department of Natural Resources LiDAR data and LiDAR portal, sorry. And the original LiDAR survey occurred between October 2010 and September 2011, with an average point density of about 9 points per square meter, and it covered 377,500 plus hectares. The LiDAR-derived DEM had a 3-foot resolution when it was downloaded, and it was in a state plane coordinate system. And we decided it wasn't a good idea to reproject it into a UTM or metric coordinate system to avoid reprojection error. And the DEM was originally tinned using TerraScan, which uses a form of Axel since 2000 densification method. Then flipping slides over to the landslide database. The landslide database was created using a protocol developed by Slaughter et al. In 2017. This protocol focused on visually inspecting LiDAR-derived slope maps. And a condensed form of this protocol, named the Streamlined Landslide Inventory Protocol, or SLIP, was what was used in this study. And this database contains a little over 14,000 unique landslide polygons, and it's actively maintained by the WGS. So how the Shi et al. Algorithm got implemented is basically the same as what was originally created, but with some slight differences. And so it was implemented using Python, using several packages such as NumPy and scikit and things like that. And only tangential curvature was what was decided to be implemented in this type, because the negative tangential curvature maps the actual body of the landslide, whereas profile curvature maps only the scarps. But that result is included with the tangential curvature. So rather than trying to merge the two outputs together, just go ahead and do the one that works. As you can see on the right side, the blue on the right side of the image where the blue is shows the negative tangential curvature at both 0.05 and 0.01 significance levels. So the raster-based version of the Getasort GI star statistic was developed in NeoPy for use for this project, the study. And the distance weighting radii for the Getasort GI star statistic ranged from 3 to 7 pixels, or 9 to 21 feet, because we kept it in a state plane coordinate system. And these parameters are actually optimized with the hill climbing technique. And to try to generate the output, the two highest bins were flagged as landslide, which means the significance intervals of 0.05 and 0.01 were flagged as landslide. And the original study area LiDAR was provided by the Hong Kong Civil Engineering Department for validation of the algorithm implementation by visual inspection of this figure from the original paper. So then the raster generation algorithm execution We had the three methods of generation, which were state provided the 10 DEM, inpainted DEM, and a SMRF DEM. And then the bounding boxes for each study area were used to clip LiDAR data using LAS tools. And SMRF and inpainted DEMs were created using Python scripts, with the parameters also being optimized using hill climbing. And the truth rasters were then created for each DEM to make sure that everything lined up and there wouldn't be any mismatch. And as you can see on the right side here is kind of the overall process from identifying your study area to executing your algorithm on how everything worked. So now results time, everybody's favorite. We have hypothesis number 1, which was the differences in the ground classification and void filling as part of the DTM generation process significantly affected the performance of the landslide detection. And that was actually proven to be that for kappa at least was not statistically significant using a Freeman test, but type 1 and type 2 errors were. And you can see that on the right side bottom with the chart with the box plots is there's not very much there's not a lot of variation with kappa, and it's incredibly low. But if you look at type 1 and type 2, there is a downward trend for type 1, which means false positive rate, and then you have a type 2, a positive trend of type 2, which is a false negative. So it shows that the inpainted and SMRF DTMs were better when it comes to like not making mistakes, as you would say. And I want to kind of cover this top image here. So this is like kind of the general result of this is study area 2, showing the kind of the lessening of less pixels being flagged as you go along from Washington DTM to the inpainted to the SMRF, kind of representing a more conservative approach as you go to the right. Then we get to hypothesis 2, and this focused on differences in type of landslide, large versus small, and how it affected the algorithm. And what the results came back were that all differences were significant. You can see that kappa is the manual is twice as high as the database, and then type 1 and type 2 are also, you have a little bit better rate when it comes to the database, but your type 2 error is much lower with the manual. So, and as you can see in the kind of these top images, you have the study area 4, which is a manual landslide identification, and it's a little more complete. Still not good, but a little more complete kind of classification of the landslide. Whereas if you go to study area 10, there's a WGS source, you have all these multiple different landslides in there, but there's a lot of empty space or unflagged pixels within the interior bodies of the landslides. And so hypothesis 3 was talking about the effectiveness of the algorithm, and it was shown to be ineffective at producing reliable results for the study areas. Kappa values are incredibly low, being 0.05 to 0.1. And it resulted in too many. It showed that too many pixels were in the scene were being misclassified. So why didn't this algorithm work well? When it comes to curvature in that calculation, tangential curvature is often used for mapping drainage patterns. And so as you can see, as you saw in those results and output images, the drainage patterns that were around the landslides and stuff were what were being mapped. And in this application, the curvature mapped both landslides and drainage patterns, which caused low kappa values, both false positives, false negatives. Large landslides had more erosional features, and these are what were picked up on and by the curvature calculation. And the tangential curvature calculations also identified mountain roads and trails as areas of high and low curvature, so that also threw off the algorithm. And then when we get to study area kind of characteristics, the larger study areas impact the overall global mean of the Gettysord statistic. And the larger study areas with large landslides could also diminish the unique signature of curvature values of the landslides. kind of representing, well, that's not very significant. Even though the landslide's large and it's a landslide, but it doesn't count. And this implies that the algorithm is overall sensitive to how big the study area and therefore the landslide is. So why didn't SMRF work well? It showed that too many ground points were left in the DTM, as well as some areas of oversmoothing. And this was caused by a lower type 1 error rate, but a higher type 2 error rate. And this implies that removing more non-ground points, potentially even some true ground points, may lead to a more accurate classification. So what could have been improved for this study? The hill climbing parameter optimization was only performed on a sample of study sets rather than a whole data set. And potentially optimizing parameters per site might have improved the algorithm result, but some limited testing showed that this effect is likely going to be minimal. And in some study areas, smaller landslides ended up being included with larger landslides, and they were potentially overlooked by the algorithm because of that global mean aspect. So improvements that I would make to the Xi et al. Algorithm is that I would definitely use more than one topographic parameter, such as entropy or slope or aspect or roughness. And then also I would use a neighborhood size larger than 3 by 3 to better calculate curvature for the different scales of landforms. And there's another mention that the surface parameters tools is available in ArcGIS Pro 2.7. So, and then so in conclusion and summarization, some major findings that there was no direct significant difference between the three methods based on Cohen's kappa. But there were significant differences in false positive and false negative rates. The 10-based interpolation method combined with inpainting for void filling gave the best balance between the three methods as being a middle of the road, conservative but not too conservative DEM generation method. And then there were significant differences in the algorithm performance between large and small landslides, showing that the algorithm was more effective when classifying smaller landslides. Recommendations for future work is I would develop a reference data set similar to the ISPR, what the ISPRS has for LiDAR classification and the cartography community has for map making and stuff for testing new and old landslide detection algorithms and to evaluate algorithm performance in different environments. And also I recommend that further study of the effects of DEM generation methods on the performance of landslide detection algorithms be done. And so I want to say thank you to my family, Dr. Pingle, for being there, helping me all along the way and helping me get to today. Thank you, Dr. Shao, Dr. Dove, for being on my committee. I'd like to say thank you to Dr. Watts for being a major inspiration for my love of geohazards and mapping and GIS and stuff. And also want to say put a shout out there for my for the Neil lab members for for me to bounce ideas off occasionally. So thank you so much for coming today. And does anybody have any questions?
Not necessarily a question, more of a comment, I guess, is that with the progression of wildfire stuff in California and Oregon State and all of them, you hear about those states in particular having severe landslides and all. Well, on the East Coast here, it's definitely progressed. Not so much we have the wildfires and all, but even with the I guess expansion of roadways and stuff, like, do you predict that becoming a bigger problem, at least from an engineering standpoint, or being important to predict and all? Or
definitely being able to predict landslides, which is through a process called landslide susceptibility mapping, which involves a little bit more extra stuff, extra parameters and stuff. I think it's, I think this is definitely kind of, so to do landslide susceptibility mapping, you need to have a good landslide inventory first, because if you don't know where landslides are, landslides can repeat, it can reactivate and stuff like that. So, it's definitely better to have a good base map, I guess you could call it, when you start doing susceptibility mapping. Does that answer your question?
Yeah, sure does.
Okay, awesome.
we'll hold for just a second if there are any more questions from the public. Otherwise, we will end this portion of the defense. Last call. All right. Well, I wanted to thank the other members that came to the talk this morning. Thanks for showing your support for Jim, and again, it was great to hear the great to hear this project kind of come to a conclusion. So at this point, we'll end the public portion of the thesis defense, and we'll move into the committee only portion. So thanks, everyone.
Thank you.